Hello friends, welcome to my YouTube channel. Today we are going to cover our next chapter, that is a symmetrical and self-equilibrated assemblies. In this module, we are going to cover our one fixture, that is a symmetrical fixture, uh, and also a shrink fit as a connection with the help of this wheel assembly. Basically, here you can see this is our wheel hub and a wheel rim. Now if you check for a interference, so if you go for evaluate and go for interference, and if you calculate the interference, you will see there is a interference in between rim and hub. This is because in actual manufacturing process, this rim has a diameter of 120 point, let's say, uh, okay, we will see that diameter in further session, in upcoming session. Now you can directly sorry, here I have simplified this model to 1/4. Here I have made one configuration regarding this. The reason behind this is that key I want to check whatever stress is going to be generated along these touching faces, because at the time of manufacturing, your rim diameter is slightly greater than the hub diameter. Sorry, rim diameter is slightly smaller than the hub diameter. Because of that, it can't fit directly on the hub. So you have to heat up the part first, and then you have to put it on hub. So after part is mounted on your hub in the room temperature, the part regain its original diameter or position, and because of that, it will create a internal stresses along the circumference of hub as well as the rim. So we are going to check that internal stresses, as well as we are going to cover circular cylindrical coordinate system to find xyz, that is hook tangential stress, radial stress, on axial stress. So let's start with this model. Now here I cut the model to 1/4 with this configuration, and uh, because I want to check the internal stress generated along circumference, which is same for all the part. Because of that, I have cut the model. Now I will start my simulation. For that, I will go for a simulation, new study, static one. Okay. Now I have already assigned the material plain carbon steel to hub and alloy steel as a alloy steel to rim. Now connection, here in previous session I have covered it, introduction to connection. Similarly, now here I want to give a connection. If you see here, by default connection is a bonded, but the bonded connection is can't help here because it's not a welded or a fixed glue part. So instead of global, we are going to create next context set, that is a shrink fit. For shrink fit, your part should have interference. So here I will go for select other, and I will select this face. Now in bottom I will select other, and I will do this face. So here you can see I have selected top face of the hub and bottom face of the rim. And here in advanced option I will go for a surface to surface contact. Here friction is not going to happen, so I didn't check that option, and I will click OK. Now my as I set the contact set, so priority is gone to contact set now. Means the global contact is won't consider here. Now in fixture, I need to fix this part. For that, before fixture apply, I have already cut the part to 1/4. So I need to apply for symmetric condition, as my part is whole circle. So in advance, if you go for symmetry and if you select this plus this edge, you will see the mirror of this part. Similarly, if you go for this and this, you will see the mirror of this whole part. So this is my actual part look like. And if you click OK, here you will see the fixtures, that is apply. I have selected this face, so fixture is applied in this direction, and also selected this face, so fixture is applied in this direction. So this symmetric fixture you can apply in such conditions where your part or whatever section, cross section is there on which you are going to apply the fixture is not crossing that plane. Means In future, deformation would not happen in this direction. Means if you apply force in this direction inside cylinder, and you have created this cutout and apply symmetry boundary condition, then it will definitely give you wrong results. So kind of make a note of it. Try to use symmetry picture only when your forces or reactions are parallel to this face, not perpendicular. So similarly for this case also, because if you see, because of the shrink fit, means here tension and compression will happen at the interference, and this hub will push the part outside. This rim will push the part inside. So it's along radius only, means along the parallel to this plane. So for external, I have not means I am not going to apply any external load here. I want to just check the internal process. So for mesh, I will create a mesh and go for a curvature base and OK. So my mesh is generated here. You can see this. Now I will go for a run study. It will run the study as you see here. Now actually here one more point is there regarding fixture which I have not applied. So I will apply first it, because my part is fixed in this and this, means along y and along z direction, but x direction is free. Sorry, y direction is free, means along axis the part can rotate. So I want to apply a different fixture for it. So I will go for a advanced fixture, and here I will fix the vertices, means this vertices for hub and this vertices for rim. And here for plane I will select the axis. So along axis rotation I want to stop, so I will go for axis selection and I will put 0. So my rotation along this direction also get suppressed or restricted. Now I will go for other study. So this is my actual result. Because of that this one machine result is on, the part is, you see the part is lifted up, but in actual condition it won't that much lifted. So here you will see the stress values around 679 Newton per m square, and for displacement will be around 0.18, which is too much small. Now here if you want to check for a circumferential, which also known as a hook stress, means along the circumference. I want to see the along the circumference stress, so you need to create a plot regarding that. And for a circumferential stress you have to first change your coordinate system to cylindrical coordinate system. For that you need one axis and the one net axis, because whenever your linear means normal coordinate system with the help of axis is going to convert into the cylindrical coordinate system, your axis will going to be your z axis for that cylinder, and along x means x direction will be your radial force, and along y is your circumferential force. So for that we will create one stress plot. Now, as I said, your x will be radial, y will be circumferential or hook, and z will be the axial. So here I will select my y, that is hook. I want to see the hook stress, and in advanced option you can select plane axis or coordinate system. So I will select here axis. So SolidWorks detect that this axis is my z direction, and along the circumference or whatever radius I have is my hoop stress. So here I will click OK. Unplug the deformation. Here you can see that your cylindrical coordinate system is automatically generated. It's not coordinating with your actual value because along z means if you see here the z is along axis. Here z is in this direction. Means you can't uh, compare your local coordinate system with your cylindrical coordinate system. Your radius will be your x. You can compare the color combination of axis. Means blue is a z, red is a x. So here red is a x and blue is a z, and along circumference is your y. So this is my hoop stress. You can see here 617. If you want to see how much tensile and compressive force is acting on the surface, for that you need to create here one uh, the vector plot, and I will go over OK. So here you can see the stress lines or stress line with the help of arrows. So this blue line indicates in anti-clockwise direction, which shows your compression force, and the red line indicates the clockwise direction, which shows tensile force. Here you can see the compressor is too much smaller. This hub is not going to compress that much, but your rim will go into tension with the high magnitude at this surface. Okay. Now I will see here what is my radial force. For that I will go for result stress plot, and here I will select now x normal stress, and for here I will select the axis, and I will click OK. So this is my along radial direction forces. This along radius, if you see the compression is too large in the circular hole region, because this rim will exert a compressive force on this hub part, and it will definitely go in less material area. So here I will go for right click, and also here change it to vector plot and click OK. So here we see the radial direction, it's coming downward, and this blue region indicating the compressive stress. Means here your compressive stress is too large. Now if you go for axial, you can't find that much. Means there will be some axial force, but its magnitude is too very small. And if you want to show this result to any other customer who don't have a Solidworks, then you can simply save all this plot as a eDrawing. Let's say uh, I will put it in document, and will assemble static as one of my part, or I can put it on desktop, and let's say I will go for a save. If you want to see that results, then you have to create this eDrawing file which I have generated. They can directly eDrawing Viewer is freely available, and it's the Viewer is a free tool. To get more function, you need to upgrade it to Pro, which is a paid version. So for to saw this result, you simply download the viewer, and here you can see the results of that plots. So here my bond basis is there. Now if you want to check for other results, uh, here you can animate the results. So this is my so that a particular person or customer can easily solve this result. You want to change for density, if you want to illustrate this strain, this radial stress, so you can easily show that by these results without a solvers also. And here I want to check one contact pressure at intersecting region. For that I will create define stress plot. In that last is my contact pressure option, and I will untick this, and I will click OK. So on intersecting region it will show me a contact pressure, you can see here, which is around 136. And if you want to see as a vector plot, then in edit definition you have to check advanced option, you have to check show as a vector plot. Okay, click OK. Now here you can see those contact pressures. Means this part exerting pressure on this, and this part will exerting pressure on this. In between, you will get a red mark where larger contact pressure is there. But if you mesh this part, then it will show you uniform distribution of the contact pressure. And if you want to see the over means complete result of your part, then in any plot, if you go for edit definition and in advanced, you will see this display symmetric result option. Whenever you use symmetric fixture, and if you click OK, you will get a result of whole part. Okay. Now we will move further, and we will work on I will copy this study because I want to show two more properties of it. So here I will use a soft spring name. Okay, now my study is already created. In this I will suppress this reference means that along axial constraint, and instead of it I will go for properties and soft spring stabilize model. This is called free equilibrated assemblies. Means this soft spring option, what it does, it basically created virtual spring along means uh, across your the whole part, and it will oppose your part to move in particular. It will oppose your part to move in a particular direction. Means which in this case, if you see along axial no force is there, so there is no need to move this part in along axial direction. So soft spring, what it does, it will act. It will fix spring to this part on this side, which are imaginary, and it will counter react that part to won't come to opposite direction. Means it basically resist part to being get deformed in with the smaller magnitude. With smaller magnitude stress or deformation, it automatically taken care by a soft spring. Means it won't allow part to move in that smaller direction, and the stiffness of that soft spring is uh, as compared to your part is a very small. Means if you apply force in this direction and if you apply soft spring, then it won't counter react this force. Means it won't fix the part in this direction. It will definitely go further because stiffness of that spring is very small. Means any small magnitude which causing a deformation in a random direction, the soft spring will taken care of it and it will constrain the body. So I will just run this study now, and at the end I will compare the results. So my study is running now. I have not changed any mounting condition. Instead of reference on I have went to I have gone to the soft spring option. Okay, so results are created. We will compare it further. I will copy this study again. Name it inertia relief. So here also I will only check one option. I will untick soft spring and use inertia relief. So basically, what it does, in soft spring, it will oppose a small magnitude of displacement, not small magnitude of displacement should not happen for that part, since it basically restrict that part. So in inertia relief, instead of applying a smaller stiffness, it will apply means it will apply counter reacting balancing weight. Means if your part is exerting a small amount of force or displacement or stress in this direction, then the inertia relief will add counter reacting weight in opposite direction, so your part will be equilibrated state. So here I have checked the initial relief part and I will go for a run. So basically you can use either of them. You can't use both means two parallelly things. The conditions are where means you can use soft swing in all cases, but for inertial relief uh, in three states you can't use a inertial relief. Basically whenever gravity is applied, then whenever thermal load is a consideration, and whenever there should be a centrifugal force, you can't apply their inertial relief because inertial relief is totally based on a counter reacting balancing rate. So gravity and centrifugal force and thermal load will give conflict to that inertial relief, but soft spring will give you approximate. So here I will compare three of results. So compare result. Here I visited all studies and I want to check for stress values only. And okay. So here you can see in my static when I apply a long axial constraint, my value is 679.1. Now whenever I suppress that option and go for a soft relief, inertial relief, my value is same 679.1, and for a soft sync it's also same. Means you can apply means if you constrain your body with your optimum requirement, but if you get any error regarding your body is not fully constrained, then you can easily use either soft spring or inertial relief option as per uh, guidelines, and you can run this model again, because every time it's difficult to constrain your model, fully constrain your model. So it's better to go for a soft spring or inertial relief. So that's it for today's session, friends. Hope you liked it and you also understood it. If you have got any query regarding this lesson or a previous lesson, you can comment down me below, and kindly share, like, and subscribe to my YouTube channel, so I will make more videos regarding the simulation, and also uh, try to provide you industrial application as well after the static analysis whole series get completed, so you will get better knowledge about actual applications also. So thank you for today's session. We will meet in uh, next session in uh, today's today's video. Thank you.